Good evening, everyone. It's my pleasure to welcome you to the Silicon Valley Astronomy Lectures at Foothill College. My name is Andrew Fracknoy. I'm the astronomy instructor here at the college, and it's my pleasure to welcome everyone here in the auditorium and those of you watching or listening on the web to this extraordinary lecture tonight. Our program features Dr. Dana Backman, speaking about a ringside seat to the birth of planets. Dr. Backman has his bachelor's degree in physics from MIT and his PhD in astronomy from the University of Hawaii. He worked as an infrared astronomer, a hot field of research, on the staff of the Kitt Peak Observatory in Arizona, and then here at NASA's Ames Research Center. His special research interests include the formation of both stars and the planets that accompany them. After teaching physics and astronomy for 12 years at Franklin and Marshall College in Pennsylvania, he returned to NASA Ames in 2003 to manage the SOFIA program. SOFIA is the Stratospheric Observatory for Infrared Astronomy, and he is the manager for education and outreach for this 747 airplane, which NASA purchased to put an infrared telescope up in the stratosphere. And I'm delighted to report that today, Dr. Backman tells me, we had the third successful flight, and even more important, the third successful landing of the SOFIA aircraft, and he will show us a hot off the press video of this brand new telescope, which we think is going to revolutionize our view of the infrared universe. So it's a great pleasure for me to introduce someone who is not only a dedicated research astronomer, but a great teacher, also an author. Dr. Backman has just become the co-author of a new textbook in astronomy called Perspectives on Astronomy, which he writes with Michael Seeds. So he is one of my favorite people, in fact, in the world of astronomy, a great lecturer, a kind person, and a terrific explainer of what's going on in the universe. It's my pleasure to introduce Dr. Dana Backman.
The topic of my talk is the topic on which I do my own research once in a while when I'm not doing my day job, which, as Andrew said, is the running the education and public outreach program for the SOFIA Flying Observatory, which is now flying, we're happy to say, and that's only been true for a month. This is an artist's conception of a debris disk, which, as I will be explaining, is a remnant of a solar system, the process of a solar system forming. And here's an artist's conception that I pulled down today from the Spitzer Space Telescope website, a very nice painting, but what these are all about, why they're significant, why they're interesting, is what I'm here to explain to you. So the outline of my talk is, first question, one that basically everyone interested in astronomy is interested as one of the central questions, maybe the only other central question aside from how common are planets like the Earth is the question about how the whole universe got its start. I think those are questions number one and number two. And so this topic is a small part of the question of how common or rare Earth-like planets might be in the universe. And since our planet is a part of the solar system, seems to be a normal part of a solar system, the only one we know a lot about, ours. Finding out about solar systems in general is addressing the question about how often other Earths might occur. I'll show some slides, some information about what we know about star and planet formation, and then get on to the debris disks, which I thought today a term might be adolescent planetary systems. They're not in their infancy. They've almost finished forming, and that they're still showing some signs of construction activity, and that's what you could put these in that place in the sequence of events of the lifetime of a solar system. And then something about the new NASA mission, SOFIA, for which I work, and actually is going to be able to address debris disks when the time comes, when we're actually doing science with SOFIA, which isn't for a few years yet. Well, here is the solar system, which has 8 planets. I got a reaction out of that. I used to say that when I was teaching at the college in Pennsylvania, and the frat boys with the backwards baseball caps, that's the only thing that would make them sit up, would be that comment of mine. I am a firm believer that Pluto's not a planet, so let me take a poll of the audience. How many of you are upset that the astronomers downgraded Pluto to a dwarf planet? Hands up. Okay, a fair number of people. How many of you are happy that this happened? I have a special interest. I wrote a textbook before they made the decision that plinked Pluto out of the planet list, and thought it was good. How many of you think this is less important than the results of the last Yankees-Red Sox game? Okay, fine. This picture, however, has Pluto in it as an object, and some of the reason why you might argue that Pluto shouldn't be classed with the planets. It'll be part of the talk in a few slides. But anyway, we have the planets of our solar system. We have 4 small rocky and metallic planets close to the Sun: Mercury, Venus, Earth, and Mars. We have 4 large gaseous or liquid interior planets: Jupiter, Saturn, Uranus, and Neptune, far from the Sun. We think we know the reason why that happened. Although we're finding other solar systems not put together that way, we think we know why our solar system is put together that way. It's not an accident, it's a feature of the planet formation process. But I'll come back to that in a minute. Here's a scale of the orbits of the planets. Pluto's tipped 17 degrees to the plane of the rest of the solar system. But our solar system, a major feature, aside from the 2 types of planets that are separated in location and density composition, is that almost all the motions of the solar system are very close to one plane. You could put the solar system on a table, basically. And most of the motions, if you viewed from one side, above or below, that there really isn't above or below, but let me get away with using those terms, the motions of the moons around the planets, the rotations of the planets, and the planets' orbits around the Sun all share the same motion, with notable exceptions. There are some exceptions, and they need to be explained by a theory of how the solar system came to be. But if you're going to try to explain how our solar system came into existence and then speculate about whether other ones might have come into existence, then you need to explain these very basic facts about our system. Well, when I was a kid, the Golden Wonder Book of Astronomy, I don't think that's the actual name, but effectively that was still giving some credence to this theory from the early 20th century that our solar system resulted from a catastrophe. 2 stars, the Sun and some other star, passed close to each other, and their gravitational pull drew material out. And as the 2 objects passed by each other, this material would have been set up spinning around each of the 2 stars and condensed to form the solid objects that we have in our solar system: the planets, the asteroids, the comets, and so on. Now, one interesting aspect of that is that this kind of collision, this close encounter between 2 unrelated stars, would have happened at most once in the whole history of the galaxy. Stars are just a long way apart compared to their size. So implicit in this picture of how our solar system came apart is the idea that we and the other solar system would be the only 2 solar systems in the whole galaxy. This would not happen. In fact, it would be a lucky chance that it would even have happened once in 10 billion years, or 10 or a little more billion years, the age of our galaxy. Yet, I've gone back and looked at textbooks from the 1920s when this was sort of at its height in popularity, and there's no, I don't know what the right word is, no regrets expressed that we would be so alone in the universe. It was just, well, there's one solar system, ours, and another one, the other stars, and the rest of the universe is sterile. No planets around stars. Oh, well. There's no, and we, all of us, pickled in Star Trek juices for decades now. This would be a very disappointing picture if this actually turned out to be true. We wouldn't like this. I certainly wouldn't like this. But people were comfortable with that, I suppose, partly because it made us very unique. Well, however, modern calculations show not just that this would have an infinitesimal chance of happening, the material wouldn't condense into planets, it would disperse instead. You wouldn't get a planetary system out of this. The stuff would just head off into the wild black yonder, and that would be it. So this wouldn't work. There's an even older hypothesis, the Nebular Hypothesis, that dates back to the 18th century, which is that planetary systems form out of some contraction process of material that's spinning slowly to start with, but then the spin picks up as the contraction takes place, the same principle of physics that causes a figure skater to increase the spin as they pull their arms in, conservation of angular momentum. And so you have a large cloud of material in space spinning slowly and contracting under its own gravity, and what you would expect, the laws of physics lead one to expect that to be a central object which has the material that had the lower spin to start with out of this collection up here, and a pancake or disk of material around it which has higher spin, and from that might condense objects, solid objects, from which you might get a solar system that's flat and with everything spinning in the same direction. So this is the hypothesis that when a star forms like the sun, you get planets as a normal byproduct. And so this one predicts that, this theory predicts that planets around stars should be common, should be a normal thing. It doesn't say how common, might be 1 in 10, might be 90% or something, but it should be a sort of a normal byproduct that you get a disk of material around the sun. And if we take our properties of our solar system and work it backwards in time to what it must have been like as it formed, you get something like one of these disks. So going forwards or backwards, the physical theories that we have indicate that this is a plausible way to make planetary systems. But if we're just arguing theories, we're not making much progress. We have to go make observations to check. Why don't we just go look and see whether there are planets around the other stars nearby, and then just take a census and then tell whether they're common or rare? It turns out it's very difficult to detect a planet. Planets are tiny compared to the sun. This is from looking from outside our solar system with a telescope and some detector that works at the same wavelength range that the human eye works at, like Hubble does. The sun is 10 billion times brighter than the Earth and 2 billion times brighter than Jupiter. You may be surprised that Jupiter is only 5 times brighter than the Earth, but it's farther away from the light source. So even though it's big, it's also not catching as much light to reflect. So looking at our solar system from outside, seeing the planets against the glare of the sun is going to be a terrible problem, and it hasn't been done yet. There may be technical advances in the next couple of decades that let this happen, but no one has spotted a planet per se that you can point to in a picture and say there's a planet around another star. Here's another illustration of that same point. Here's a nearby star that I'll be also talking about later on in the presentation. Its name is Epsilon Eridani, which means it's the 5th brightest star in the constellation Eridanus, the river. Not a very prominent constellation, but it's a long, sinuous chain of stars that starts out near the foot of Orion and goes down south from Orion and Taurus. So Epsilon Eridani is in the same part of the sky as Orion, a winter sky. It's a star that's a little bit cooler and smaller than the sun. This is an image from the ground at, again, visual wavelengths, human visual wavelengths. This little bar here shows you the size of our whole solar system. That's the diameter of Neptune's orbit on the scale of this picture. This is not the star. The star is not huge. This is the burned out image that results mostly from the turbulence of the Earth's atmosphere, but also the way light bounces around inside of a telescope smears the image inevitably. Now, if you're thinking along here, you might say, well, use a space telescope. I mean, what's Hubble for if it's not to get above the effects of the Earth's atmosphere? But there's an unavoidable smearing of light that occurs even for a space telescope, just by the physics of what happens when you try to put light waves down a aperture and try to bring them to a focus, you smear the light. The effect is called diffraction. And the diffraction pattern, the smeared light at the focus of the Hubble Space Telescope for looking at nearby stars is still bigger than their solar systems would be. So even with Hubble and getting rid of the atmosphere of the Earth, you still have this other effect called diffraction that makes it so you can't see the planets around nearby stars, especially with that horrible contrast level of billions to 1. Well, okay. There are other ways people, as you know, people have detected planets around other stars. The mass ratio is a lot more favorable. The Sun is only 300,000 times the mass of the Earth. It's only 1,000 times the mass of Jupiter. Instead of working with factors of 1 billion, you're working with factors of 1,000, and this gives you some leverage, some ability to actually detect the planets. And that's what's been done. As the planet goes around, it's not proper to say the planet goes around the Sun or the planet goes around the star. They both go around a mutual center of mass, which is here. Now, that center of mass is very close to the position of the star because the planet is tiny still compared with the star. But what's actually happening as the Earth goes around the Sun is executing a very tiny wobble, very tiny because the Earth isn't very big. Jupiter makes the Sun wobble quite a bit more, and it's in time with Jupiter's orbit. So Jupiter goes around the Sun in a little more than 11 years, and the Sun executes a little wobble in response to Jupiter's gravity. And you can detect that. People have detected it in 2 different ways. The less feasible way, the way that hasn't worked as well, is to actually just take a bunch of pictures and look for the motion of the image of the star. A better way is to look for the Doppler shift. That means looking at the spectrum of the star and seeing that sometimes it's blue shifted and sometimes it's red shifted as the star rocks back and forth, coming towards us and away from us as its planet or planets go around it. And that has succeeded. As of day before yesterday, I looked at the Extrasolar Planet Encyclopedia webpage. 236 planets had been detected around other stars. The first of them was in 1995, and so in 12 years, we've by the star wobble method. So you're not actually seeing the planets, you're seeing their effect on their parent stars, but the census is now up to over 200 extrasolar planets. However, most of these systems are not arranged like ours. They almost always have planets sort of Jupiter-sized or even bigger in orbits that are close to their parent star, closer than Mercury is to the Sun. So you've got Jupiter's in where Mercury is supposed to be, so to speak. And I have to go back and apologize to 200 students to whom I gave final exam questions about how the solar systems are supposed to be arranged when we finally do find them. Is it going to be the big planets in the outside and the small ones close in? There were reasons to believe that, at least from our system, and the first couple of 100 solar systems we found aren't put together that way. However, we think it's a selection effect, and this is a talk for someone. This is not the main subject of my talk. Other people have addressed this in this hall before. It's a selection effect. The first planets you would find by looking for star wobbles are the big ones close to the star. We think there's plenty more of big planets and small planets farther from their stars in systems that have architectures more like ours, but the jury's still out, and the scientists are refining their instruments to go look, to be sensitive enough to see systems that are put together like ours instead of these strange hot Jupiter systems. Well, so we know that stars make planets in some sense, although not necessarily, we don't know for sure how often it looks like our system. I think the total sample of stars that have been searched is in the 2,000 range. So 236 out of 2,000, we're getting to be 10% or so of the stars searched. And the searches continue. That number's bound to go up. Well, so one of the methods of finding out whether planetary systems are common or rare then is just look for the planets, but that's very technically difficult. Although there's been some success, we're finding Jupiter and Saturn-sized planets galore. How about looking for the solar planetary systems forming? Now, you can't The time it takes for a planetary system to form, we calculate, is longer than a funding cycle. So scientists can't really wait for that to happen. But you can find one stage over here, another stage over here, another stage over here, and work out what the story is, what the sequence is. Is it A, B, C, or is it A, C, B, D, whatever? And that's what we think we can do. And that's easier, technologically easier, less challenging so far than finding actual planets. Here is, and I'll go into one of the ways that's done. This is a cartoon of the discovery of infrared radiation by William Herschel, the same astronomer born in Germany and spent his career working in the United Kingdom. This is the same person who discovered the planet Uranus, which he first said he proposed should be named George. Actually, Georgium Sidum in Latin, meaning George's star. And why would that be? Anybody care to hazard a guess? The king, the paycheck, yeah. Wiser heads prevailed, and the Greek and Roman pantheon got used for Uranus. So we were saved from Mercury, Venus, Earth, Mars, Jupiter, Saturn, George. But here he is in the year 1800 with an experiment. This is a cartoon because he would not have had the window open to his backyard with his big telescope in the backyard that he and his sister mapped the heavens with, his Charlotte. Here is a big telescope, and here is a wooden stage on which he has 3 thermometers, and he has let in a beam of sunlight through a prism you see up here behind him. So the sunlight has been split into its component colors on the table, and he's using the thermometers to crudely measure the different intensities of the different colors as best he could with the technology he had in hand. He's portrayed as a good scientist because he has a control thermometer outside the sunlight beam, so in case it gets warm in the lab in the afternoon, then he will know that that's due to the conditions in the, change in the systematic conditions around. So anyway, so he's moving these thermometers back and forth in the sunlight beam, and he slides it off the red, beyond the red, where his eye sees nothing, but the thermometer says there's something. That's just as much there as the colors further over that you can see. So he named this infrared light, meaning beyond the red. So this is the discovery that there's invisible light. Your eye can't see it, but the thermometer treats it just the same as the rest of the spectrum. He didn't discover ultraviolet light the same day because ultraviolet doesn't pass through the glass prism. That had to wait for a few decades before somebody found that there was ultraviolet stuff beyond the other end of the spectrum. Okay, this is actually a homemade Herschel experiment. You can get a shoebox and some dime store thermometers, paint the bulbs black, put in an Edmund Scientific prism, and then here's a spectrum of the sun, and you can go and do and they respond over beyond the red. So you can do this. Instructions for this are on the Caltech Cool Cosmos website. I can tell you the web page later on. This is a classroom exercise that the Spitzer and Sophia Education Public Outreach Office have put together. Anyway, so now we know that aside from visible light is just a tiny slice of the possible types of electromagnetic radiation. These are all the same physical phenomena. The frequency and the wavelength are different, and our eyes only see a narrow slice in the middle. If you'll let me mix my metaphors a little bit, if this were a piano, we're only detecting 4 keys in the middle of the 88 keys of the piano. And the names are arbitrary, the divisions are arbitrary. There's nothing that says it has to be that's different to the left of the line between gamma rays and X-rays and so on. Those are human names for all of those. But anyway, infrared is the slightly longer wavelength and slightly lower frequency radiation than what your eye can see. And it's proper actually to call it all light. Some of it's visible light, some of it's invisible light. And NASA set about 20 years ago to put into orbit a set of observatories that would be addressing different parts of the electromagnetic spectrum because you see completely different views of the universe depending on which type of radiation you choose to collect and analyze. The Compton Gamma Ray Observatory, the Chandra X-ray Observatory, Hubble, which is ultraviolet, visible, and near-infrared, and Spitzer, which is the most recently launched of these, launched in August '03 into orbit around the sun. So that's an infrared observatory, Spitzer. To make a long story short, these different bands of the electromagnetic spectrum are produced primarily by objects at different temperature. So, for instance, an X-ray observatory is most easily detects things in space at that are 1,000,000 degrees. So those kinds of observatories, the X-ray observatories, are looking at catastrophes, exploding stars, material going a whirlpool down into a black hole just before it disappears, gets up to 1,000,000 degrees, and so on. A Hubble looks at things that are the temperature of the sun that make light, that at the same wavelengths our eye can see. Spitzer is sensitive to things cooler than stars at a few hundred or at most a few thousand degrees Kelvin. And those are the phenomena that you use an infrared telescope to study. So, in fact, as you're making, we predict, and have found out to be true, as you're making a planetary system, these intermediate stages before you're finished with the finished planetary system, these intermediate stages are strong infrared sources because you've got a lot of surface area of material, lots and lots and lots of square meters of stuff spread out that hasn't been consolidated yet into planets. It's a consolidation process as far as we understand, and it's not as hot as a star, as a finished star, so it'd be in the few hundred to few thousand degree range. So these, stages B, C, D here at least would be easily detected as infrared sources and not visible light sources. So in 1983, the US, the Netherlands, and the United Kingdom collaborated to put a small infrared space telescope up called IWrasse. And what IWrasse did was make the first far infrared map of the entire sky. It swept the whole sky 3 times in the course of a year. It stopped working when its liquid helium ran out that was chilling the detectors to just above absolute zero. And this was sensitive to radiation that doesn't reach the ground. Infrared, that's an important point for later. Infrared radiation, most of it doesn't reach the ground. Near infrared, which Herschel was detecting, does, but most of the infrared band, the Earth's atmosphere is opaque. So I have to put up a balloon, a high-flying aircraft with a telescope, or a space telescope to really look at most of the infrared radiation coming from the heavens. So that was about a 24-inch diameter telescope. Here is a view of, this is to just illustrate the point how different the universe looks. This is Orion as you would see it with your eye minus the convenient blue lines, which here. And so everything you see in this picture on the left is about the temperature of the sun, as ordinary stars, making light that the human eye can see, and other eyes in the animal kingdom, And on the right, this is a picture in the far infrared. Actually, it's a composite of IWrasse data. IWrasse actually didn't have imaging technology, but it scanned the whole sky, and then you could recompose that into images, pseudo-images like this. The different colors represent different intensity, not different temperatures. Everything glowing in this picture is at a temperature of about 50 to 100 above absolute zero, so several hundred degrees below zero in our ordinary temperature zones. And what you see, the strongest radiation from the bright yellow places there, those are star-forming regions. Those are places where stars are coming into existence right now. And that is one of the main things that infrared astronomy studies, is the process of star and planet formation, because the material is not yet as warm as a star, and you have strong infrared sources. Now, once IWrasse found where the strong pinpoints of infrared radiation were, then Hubble could go take a look at those spots with a much bigger telescope and with a finer ability to see finer detail. This is a picture of a tiny piece of the Orion Nebula. So I'll go back to the previous picture. The Orion Nebula is this large bright yellow place down below Orion's belt here. This next picture is a tiny patch of that nebula, and what we see silhouetted against the glowing gas of the nebula are these sort of disc-shaped little things which turn out to be the size and the mass of a solar system forming. So we found several hundred of these now. They go by the kind of, to me, unattractive name of proplyds. What they are disks of material around stars. Is that one of them seen here edge on, one's seen sort of face on, but what's embedded in the middle of it we can tell is something that's got the properties we expect of a star that's in the process of forming. And here's another one of these, and it's near a big hot bright star off the picture that is actually hot and bright enough to be evaporating this gaseous disk and be destroying it, and what you're seeing is the cloud of material leaving it. So we have found, using IWrasse to pinpoint, to detect them, and then Hubble to get images of them, we have many examples of what we're just completely sure are examples of planetary systems, solar systems forming. Here are a few that are edge on. So what you see is a bar, opaque bar of material that's the plane where the planet's material is coalescing, hiding the star, but the star's light is kind of sneaking out through the top of the disk and lighting up some material that's nearby. So you're seeing the starlight, can't see the star, it's hidden behind the bar, inside the disk, but it's lighting up material that's in the vicinities. These were taken with a high resolution camera on board Hubble by my friend Carl Stoppelfeld at JPL. But now here's the main topic of the talk. One of the unexpected, it was fair to say they expected to find evidence of star formation with IWrasse. It just sort of had to be, but they didn't expect this one. But these are the data from IWrasse. IWrasse did not make images. You could recompose images after the fact, but what these data are, these are 4 graphs for 4 different stars that IWrasse looked at, and they show the intensity of radiation coming from IWrasse, detected by IWrasse, coming from these 4 stars, Vega, Fomalhaut, Beta Pictoris, and Epsilon Eridani, at 4 different infrared wavelengths. So that's what the 4 data points are, and the diagonal lines show what the amount of radiation coming from the star itself should be. So these are exponential plots. Over here, Beta Pic, you see that high data point, 400 times as much radiation coming from Beta Pic's vicinity as from the star itself. And in the case of Vega, that's the plot in the upper left, there's 10 times more radiation coming from there than we expected from the star alone. And we're sure about the models of the stars. Also, plenty of stars were normal, didn't show this kind of strong excess infrared emission. This is from material that's at temperatures of like 50 or 100 degrees above absolute zero around these stars. And they thought they broke the satellite, actually. I worked for Fred Gillette, and Vega was used by all infrared astronomers as the standard star. The first thing you do is point at Vega to check your equipment. So they pointed at Vega with IWrasse once it was in orbit, and it's returning this information that it's 10 times brighter than it's supposed to be, and they thought something was seriously wrong, that the resistors weren't resisting or the capacitors weren't capacitating, and but then they looked at some other stars which were normal and concluded that Vega was not what it was expected to be. So these were the first 4 reported by Gillette in 1984, the fabulous 4 debris disks, the brightest, closest example of this phenomena. The letters after the star, A0, A3, A5, K2, you may not be familiar with those. Those are the types of stars. So Vega, Fomalhaut, and Beta Pic are brighter and hotter than the sun, and Epsilon Eridani is a type of star that's a little cooler and smaller than the sun. This is the Washington Post headline based on the press release in 1983, August 1983, after the Vega discovery was made. The point was that the calculation could be made easily by the astrophysicists here that the dust that was being detected by IWrasse, the material that was making that infrared excess, which is just gravel and dust and so on around Vega, heated up by Vega, and then we're getting the infrared, the heat radiation from that surrounding material. That material would be destroyed quickly by several different processes, quickly compared to the age of Vega, which astronomers, it's not too easy to work out the age of an individual star, but there were various ways to estimate the age of Vega. The lifetime of that material was much shorter than the age of Vega, so it couldn't be leftovers from Vega forming. In fact, it had to be material re-released somehow that had been incorporated into bigger things. And now we're seeing dust, for instance, from collisions of asteroids, collisions of comets, or active comets dropping off their loads of sand as they go around Vega. And that was the same calculation was true for the other three of the Fabulous Four and other examples of this thing. Well, Fred Gillette gave this talk in Tucson in 1984 at a conference called the Protostars and Planets meeting, and I was lucky enough to be in the audience. And people ran out the back door and called their friends who were Brad Smith and Rich Terrell, who were in Chile at an observatory with a device called a coronagraph. It's a little metal mask in front of a camera to block the light from a bright object to look for faint things around it. Doesn't work too well for planets, but you can see, for instance, they were planning to look for new moons and rings around the planet Uranus with this. And somebody said, Gillette just made this announcement. Would you go point your coronagraph at Beta Pictoris, which was the strongest signal of the Fabulous Four? And this is what they saw. So this central thing here is actually a blocked out, a combination software and hardware blockage of the star, and sticking out like wings, sort of like a clam with wings here. Okay, so these wings here are the material around the star that is in a flat plane that is giving off this strong infrared signal that's much, much brighter than the star. Now you say, well, isn't this like those previous examples of those proplyds in Orion? Well, this star Beta Pic is not forming, it's finished forming. It's, and also it's not in a star forming region, it's a mature solar system. And secondly, although it doesn't look like it in this picture, this is very transparent and there's no gas. So this is just solid material, no gas mixed in, and it's transparent, and the signal, 400 times brighter than the star, and the total amount of material is just equal to our moon. If you pulverized our moon and turned it into grit, into sand, the signal from that would be hundreds of times brighter than the sun in the infrared as seen from a distance. So if you want to detect not planets, but the construction material for planets, or the leftovers from construction material for planets, here is the way to do it with the infrared signal. Well, anyway, people used other types of telescopes. This is a sub-millimeter telescope, is basically a radio telescope, or it works in the zone between radio and infrared. This is from the ground, and these were the first actual images of the other debris disks, Vega and Fomalhaut, and also Epsilon Eridani. This is the radiation coming from material that's very cold compared to room temperature, but is warmer than space, that is surrounding these stars, and is, well, what is this stuff? Why do these stars, which are mature formed stars, not in star-forming regions, why do they have this stuff around them? Well, people started to looked in the literature, and there was a suggestion made way back in the 1950 by Gerard Kuiper, and also we found later independently a geologist named Edgeworth, who suggested that there should be stuff beyond the planets in our solar system. There should be leftover material that didn't get consolidated into planets. There should be a sort of a raggedy edge to the solar system beyond Neptune. And this is a plot they made of how much stuff was needed to make Jupiter, Saturn, Uranus, and Neptune. That's what the 4 bars are. And if you just continue the graph on out, you see that there is, as Kuiper said, why should there be a sudden drop-off at Neptune and then nothing beyond it? They knew about Pluto, but Pluto is so tiny that it isn't as much stuff in Pluto anywhere near as in this tail of this graph that you look at and say, well, shouldn't there be material beyond Neptune? If not another planet, the raw material for another planet. So this is, was found, the first material, well, you could call Pluto the first material in the Kuiper Belt, discovered in 1930. But starting in 1992, we began discovering other objects in the Kuiper Belt. And here's an artist's conception of the Kuiper Belt. It's not very accurate because the latest data on the Kuiper Belt indicate it doesn't go as far out from the sun as this. But what you're supposed to be seeing here, this is a view, the planets of our solar system are the purple circles, purple ellipses in the center here, and the rest of this is a zone of small objects like comet-sized, 1 kilometer, 10 kilometer sized objects that is outside of Neptune's orbit, extending out quite a distance from the sun. We now have found approximately 1,000 objects in this zone, and Pluto is now the second biggest. So that's, for astronomers, that's one of the, Pluto is just the second biggest so far. Who knows, in 10 years it might be the 4th biggest known piece of stuff in this zone. So Pluto, had Pluto been found to have other companions and other objects in the same orbit with it, like the asteroid Ceres was discovered in 1800, and within 4 or 5 years, half a dozen more asteroids had been found, and no one considered calling Ceres a planet after that. It's just one object in the biggest object in a zone. Well, here you have this zone, Kuiper Belt, and Pluto is the second largest, and someday may be farther down the rank than that in here. The debris disks around the stars, around the fabulous 4 stars, are the right size and the right mass to be the dust associated with young Kuiper belts. So that's making a long story short. When you're seeing here, our Kuiper Belt, we estimate now, has 100 million objects in it. It's much more populous than the asteroid belt between Mars and Jupiter. And what you're seeing here around the fabulous 4 stars, and now quite a few more stars that have been investigated, is basically their Kuiper belts, which are easier to detect. Ours is fairly sparse now, but once upon a time there was more mass in it, and you would have seen a strong infrared signal from our solar system when it was young, but the planet formation process had finished. What you're seeing then are planetesimals, what we call. That's the term for planet building bricks. Here's, I basically jump over. This is just another one, not one of the fabulous 4, a star that's only got a telephone number for a name, HR 4796, that has, and this ring of material around it, that I was part of the team that made these images with the Keck telescope, and it has a ring that's about the same size as the Kuiper Belt, with an empty zone in the center. Okay, now, question might be, how do these evolve? Here's a young system. Here are these sort of 10 million year old proplids in Orion. This is Beta Pic, which is, its age varies, depends on who's doing the estimate, between 20 and 100 million years, but that's long enough for the planets to have mostly finished. And our solar system still has dust in it, and the dust between the planets in our solar system can't be leftover dust from the solar system forming, because all the processes, as I've been saying, there's several processes that should sweep the dust away in a short time compared to the age of the solar system. So I've been lucky enough just once to see the zodiacal cloud. I was on Mauna Kea. It was extremely dark. What you see is a flame-shaped glow above where the sun had gone down an hour earlier. As I've seen it. Has anybody been? No, I think. Oh yes. All right, a couple. You need very clear skies and a very dark night, but what you're seeing is the dust in our solar system, which is chips of asteroids and chips of comets. So the material was embedded in these larger objects for 4 billion years, and then the comet comes near the sun and vaporizes and drops some of its sand that's embedded in the ice, or 2 asteroids hit and shatter, and small pieces of material are released. Well, let me move along here. This is the Spitzer Space Telescope, which is a much more powerful successor to IWrasse. Well, after all, look at how big it is. It's bigger than the Earth, so it's a really big. It's an 85 centimeter telescope. It's I think that works out to be 32 inch. Again, it's cryogenically cooled, and it's in orbit around the sun, so it doesn't have the warm Earth shining on it to boil away the liquid helium. So it's got a 5.5-year lifetime instead of IWrasse's 1-year lifetime. And so I was part of a team. This is how astronomers do their business a lot of the time these days. This is a team of 20 or more scientists spread all over the world working on one project together and publishing our papers and taking turns being the first author on the papers that come out from this. So this is the Formation and Evolution of Planetary Systems Legacy Project to use Spitzer to look at 350 sun-like stars of various ages to see whether we could detect their Kuiper belts and maybe their asteroid belts over time. And what we found was 15 to 20% of stars at the detectable level of Spitzer show some signature of having a Kuiper belt around them. There could be other ones, but they were just not strong enough for Spitzer to pick up. The average amount of dust seems to decrease with age, but sometimes there's some older systems with a big, strong signal, and we wonder if that's where there was suddenly astronomically recently, a big collision releasing a lot of material that then hasn't been cleared out yet by these processes that clear it out. Only a few percent of the stars showed detectable sort of Earth-Mars temperature material like the warm asteroid belt in our solar system. So the asteroid belt would qualify as a very thin old debris disk, and our Kuiper belt would qualify as one. And we found plenty of stars have Kuiper belts, plenty of stars have asteroid belts, and there's some overlap between them and the stars with planets, although the statistics weren't very good. Well, now let me go on to my second to last point here, which is about what, aside from it seeming reasonable that these are the leftovers of solar systems forming, can you use the debris disks to actually say, for sure, there's a planet in one of these systems? The planets orbiting these stars have gravity, and that gravity can change the shape of the dust belts around the stars, and that is why we've gone and done some of this work. This is a much deeper exposure of Beta Pictoris. This black central region here is, like I said, again, a combined software and hardware mask to block the light from the star. And you can see, even from where you're sitting, that this is not symmetric. It's got wiggles and warps. The two halves of it aren't the same size and shape. The lower left and the upper right are not symmetric to each other. The only simple way to make those kinds of warps and wiggles and asymmetries in something like this is to have it be the result of the gravity of planets going around Beta Pic that are stirring up the dust and causing the distribution to not be even, to not be smooth. This is a close-up of Beta Pic with one of HST's instruments showing this, that the disk has got this real wiggle or warp in it, but people using the next generation camera, which just died 2 weeks before its warranty ran out on HST about a month ago, using the ACS camera. This is an image of the Beta Pic disk, and you can see how precise and high resolution the camera is because how thin the disk appears. Can you see from where you're sitting that there's the main disk, and then tipped a little bit relative to that, there's another thin disk. There's the main disk, horizontal, and then tipped like this, there's extra material. My pointer's not doing too well, but I'm showing it. It goes from lower left to upper right, tipped. The only simple way to have that happen is there's a big planet orbiting Beta Pic on a slightly tipped orbit relative to the other material there, and some of the dust is caught in the orbit of the tipped planet. That's dynamically that's the most reasonable way to make it. Here is Epsilon Eridani. This is a close-up, and this star, actually I'm trying to write a paper on this between midnight and 1 in the morning is about when I get my chance. This is the radiation from the Kuiper Belt, the dust in the Kuiper Belt of Epsilon Eridani, that same star I've been showing. It's a nearby star. It's only 10 light years away. This lower right shows you the size of Neptune's orbit and the resolution of the telescope. The smallest detail that the telescope could see is that circle in the upper right. So this is a view from a ground-based sort of radio telescope on Mauna Kea. Take a look at that versus this. This is a model that was calculated for what our solar system would look like from the outside, given the dust in the Kuiper Belt being affected by the gravity of Neptune. So here's Neptune. Neptune's orbit would cause there to be an accumulation of material at what's called the Lagrange points ahead and behind of Neptune in its orbit. And when I look at that model of what our solar system should look like from the outside, and then I look at this real image of Eps Eri, I see a lot of resemblance. None of the techniques we have can possibly detect a Neptune-sized planet this far from a star because the wiggle takes 200 years, right? You're not going to do that. But here is a way to infer that there must be planets. A system perhaps like this drawing where you have the planet parked and perhaps sculpting the inner edge of this debris zone. This is a picture with that same camera, ACS camera, that failed on Hubble of the other fabulous 4 stars disk, and it's a very narrow ring, and it's not even. There's parts of the ring that are brighter than other parts. Again, the simplest explanation for why the ring is offset. Oops, we got another one. Okay, whoa, here's the ring. The ring is fairly narrow, and the simplest way to explain why the ring is so narrow is to have a planet orbiting perhaps just inside of it here and maybe another one outside. But the influence of the planets may be seen in the fact that the ring is not smooth, but it's got places where there's more or less material. That's called shepherding, and in Saturn's rings we see a similar phenomena where the gravity of Saturn's moons cause there to be places in Saturn's rings where there's more or less material, and we may be seeing a similar phenomenon here. There isn't any other really reasonable physical way to make the ring have these asymmetries. It's off-centered of the star, so it must represent an off-centered, an elliptical orbit of a planet, and it's got unsmoothnesses, asymmetries in it that we think are clues to planets. So let me jump to here. This is data that I took with Spitzer, and it just looks like op art, I know, but what this data represents, this is the strength of the infrared radiation versus wavelength at wavelengths of 10, 20, and 30 microns, where the human eye sees about 0.5 microns wavelength. So the human eye's sensitivity would be way off the left of this chart. This is in the mid-infrared. This, I'm not going to go into the great detail, but this shoulder and plateau here indicates there's material around Epsilon Eri at exactly the same position as our asteroid belt. This is the infrared radiation, not from a Kuiper belt, but from an asteroid belt around Eps Eri, which we've now found with, and the shape of this sort of shoulder here says that it's silicon, it's silicate, it's sand. It's not icy material. I should have said that. We have, in the same investigation, we've shown that the stuff out here is icy material, like cometary stuff, like in outer solar system. And this is an inner asteroid belt. So, and there's a planet candidate, a planet wobble around Epsilon. So what we're developing is this picture that Epsilon is very similar to our solar system. It's got a Kuiper Belt, it's got an asteroid belt, and that asteroid belt is next to a Jupiter-sized planet. So this is perhaps the closest we've come to a system resembling ours. The age of this star is just slightly less than 1 billion years old, so it's somewhat younger. It's a quarter or a fifth of the age of our sun. Okay, so let me go on. So now SOFIA, my day job, this is an infrared telescope, 2.5 meter infrared telescope in a 747 SP, which we bought used from United Airlines. The contract said at the time this plane was bought, actually it was economical to fly beef on the hoof into Japan, and our contract said we didn't want one of those airplanes. Think about it for a minute. And so this is a special long-distance stubby 747 SP. This is a slightly larger than Hubble-sized telescope in the back behind a door that opens. And we expect, when we're finally fully operational several years from now, 140 flights per year. It's 20% shared with the German space agency DLR. And this observatory has features to specifically designed for education and public outreach, which I'll explain in a second. Well, it went the wrong direction. This is a cutaway view. The astronomers' work consoles would be here, but also for educators on board as guests working with the astronomers. A pressure bulkhead here. So this is a shirt sleeve environment. The telescope is back here, open to the stratosphere once you get up to the stratosphere, above the water vapor that blocks infrared radiation. And so here we go flying SOFIA. It's, in terms of how much infrared radiation it can collect, it's 80% of the way to being a space telescope, but it comes home every night. So, and nevertheless, NASA canceled us last year, and we got Congress to put us back in. So, yeah. What SOFIA can do, SOFIA is not just aimed at debris disks. It's one tiny part of it. SOFIA will be a general observatory for astronomers all over the world, collaborating with American and German astronomers to do any kind of project, galaxies, planets, star-forming regions, whatever. But here is a Spitzer image of the debris disk around Vega, which doesn't look very interesting here. But because Spitzer's smallest detail, you see, is this circle in the upper right, compared to, this is what the SOFIA cameras will be able to see details this small, because SOFIA is a bigger telescope. It's a 3 times bigger telescope than Spitzer. And although it's not chilled, it's not in space, and it's not, the mirror is not chilled to absolute zero, we nevertheless can compete with Spitzer and do better than Spitzer in some fashion. And if you can see details this size in the Vega debris disk, then you have a chance of seeing whether there are planets warping that one as well as the other ones that we have some evidence. So this would be one of a type of project that I would, for instance, want to use SOFIA for. This is the Kuiper, which was the predecessor to SOFIA that flew for 20 years based at NASA Ames at Moffett Field. And in the last 5 years of the Kuiper's existence, Edna DeVore, now at the SETI Institute, ran a program to have teachers on board working with the astronomers. Here's an astronomer, here's an astronomer, here's a teacher, here's a teacher, and here's a journalist from the hometown of the teachers on board, seeing how science really works. And it's not like the scientific method circle in the front page of your textbook. It's blood, sweat, and tears, but this is a chance to really see what it's like. I myself only got to fly on the Kuiper twice before it was retired, and it was not a comfortable environment. SOFIA will be very comfortable in comparison, but here we had 2 of the 50 teachers who flew on board the Kuiper. And if any of you are teachers or you have friends who are teachers, here's my cult literature. My job will be to train teachers to go on SOFIA and work with the astronomers. And here is our vaporware. It's very generally described yet because it's a few years off, but I have a stack of them up at the front of the on the stage if you want them. Also, I have a stack of SOFIA stickers if you'd like that. So I am almost done here. Then I'll show my last slide, which is the pay dirt. Not that SOFIA can do this, and not that Spitzer can do this, but we're leading up to someday being able to point to a pale blue dot. What you're seeing here is the Earth, that really is the Earth, seen from the Voyager 2 spacecraft, looking back from the Kuiper Belt, which is where the two Voyagers are now, sailing out the solar system through the Kuiper Belt. And we have maybe 15 years, 20 years to wait until we might be able to point to a dot and say that is an Earth-sized, Earth-atmosphered, Earth-temperatured object around a star like the Sun. And that's where what it's all about. This debris disks are just a little piece of figuring out how often that might happen. So I'm done with my main talk, but what I want to do is show you a couple-minute movie of SOFIA's first flight, which was 26th of April. The NASA Dryden is going to be down in Southern California will be the location of SOFIA's operations, but the Science Center for SOFIA will be up here at NASA Ames. And this movie is a collaboration between Dryden and Ames. Here's the plane. When the plane gets even with you and a little bit past to the right, you'll see a bunch of people standing on the runway apron. One of them's me. There we are. That was a high moment because we've been waiting 10 years for it to finally take off. It took a long time to modify the plane, twice as long as we expected. Here it is. This is the view from the chase plane. This is Carla Thomas, the photographer for Dryden, who does chase plane photography. I thought that's a pretty cool job, actually. So the chase plane is going under and over and around SOFIA to make sure everything's fine. The telescope door is not going to be, I'll stop this. Maybe I'll play that again. What would you say? And as Andy said, the third flight and the third landing took place today. Another week or two, and it's in Texas now, where it was modified at a communications, at an aerospace company that modifies planes to put spy gear in them usually. I guess a telescope is spy gear of a sort. Anyway, yes, boy, off we go. I think that's me screaming in the back. Anyway, the pilot was Gordon Fullerton, an ex-astronaut who flew the shuttle into space twice and also flew the drop tests of the shuttle landing at Edwards Air Force Base before the first shuttle orbital flight. Fullerton is the only pilot who ever landed the shuttle at White Sands in New Mexico, because there was that flight, both Edwards and Kennedy were weathered out, and White Sands is at like 7,000 feet, and so he slammed it into the tarmac and bent the gear and blew all the tires on the shuttle, and so we were worried, you know, the takeoff looked fine, Gordon, but how about the landing? The telescope actually complained a little bit about the telescope accelerometer didn't like the takeoff, but it was okay with the landing, I guess. Anyway, so all right, so I'm done, and I'll take questions now. Well, I went a little over. I'm sorry about that. But
thank you very much, Dana, for the wonderful talk and the movie, which is, I guess, a hot off the press movie. And we're now going to invite people to ask questions. We have 2 microphones set up in the center of the auditorium, and I'm going to ask Dr. Backman to go back and forth between the 2 microphones democratically. So if you have a brief question, Please line up behind one or the other of the microphones, and Dr. Backman will take them in turn. And I'll leave it to you.
Okay, well, we'll start here.
Okay, 747 is certainly not no Blue Angel, and also you have turbulence there. How do you keep Sophia aimed?
The telescope is vibrationally isolated from the rest of the plane. The question was, how do we keep it aimed? The telescope is floating on an oil bearing, a spherical bearing, with a pneumatic system that's isolating it from high-frequency vibrations, but also there's an optical camera mounted with the telescope looking at the piece of the sky we're looking at, and a tracker camera and a tracker operator to sort of joystick and keep us pointed. But also the telescope control computer talks to the autopilot, and so the sweep of the telescope as the Earth turns is taken care of by the plane flying a very long, slow arc. So you've got 3 different levels of control of pointing the telescope in the direction it needs to be going for science. But you wouldn't believe this could be possible, except that we did this for 20 years with the smaller airplane and the smaller telescope on board the Kuiper, and it worked just fine. The images quality is like a ground-based telescope. Yes, sir.
I was vaguely aware of the Kuiper Belt before, but I'm also aware of the Oort cloud. What's the difference between the two?
The Oort cloud is, as far as we can tell, it's spherical, and it's much farther away. So it's material that was thrown, the Kuiper Belt is material that has basically always been where it is and is just leftover stuff that didn't form into a planet because it was too sparse or Neptune stirred it up. So the Kuiper Belt has been where it is now. The Oort cloud is material that astronomers think was raw material in the Jupiter-Saturn zone, and Jupiter and Saturn got so big that they tossed this stuff almost completely out of the solar system into a spherical shell around the solar system. So the distance between the Earth and the Sun is 1 AU. The distance from the Sun to Neptune is 30 AU. The Kuiper Belt goes from about 30 to 80 AU, and the Oort cloud starts at 10,000 AU. It's a tenth of the way to the next star. So and spherical as far as we can tell, because the comets, those Oort cloud comets, come in from all directions. Okay. Over here then.
Do you think that the number and arrangement of planets in our solar system is a fluke or the norm?
That's a great question. The question is the arrangement and number of planets in our system a fluke or a norm? You would think, given what we've found in the first 10 or so years of finding planets around other stars, that we are a fluke, because almost all of the other systems are arranged with hot Jupiters near the Sun. But we think the explanation for that makes sense given other things we know, is that those planets migrated, that they formed where Jupiter was supposed to form, and there was enough residual disk of raw material that there was actually friction, viscosity, and the Jupiters that formed a little too early migrated in. So our system was one where the Jupiter formed late enough that it didn't migrate. Now, the question that begs is, so does that happen normally? Is the migration normal, or is the non-migration normal? And the longer astronomers measure these star wobbles, the more systems they find that look more and more like ours. So the trend looks like the hot Jupiter systems are weird and we're normal. But the jury's still out. So it's actually an exciting question. The question is not answered now, and in about 10 years we'll have solid information about whether our system's the strange one or our system's the typical one. So it's trending towards us looking normal, but not, you have to wait.
And do you think that, for the other half of my question, do you think that it's normal to have 8 planets, or is it more usual to have like 2 or 3?
Oh, that's a good, I don't think anybody knows the answer to that. When people do simulations of solar systems forming, computer modeling of it, which there isn't good reason to believe that the models have good fidelity, right? So you don't know yet whether we know all the considerations. We got surprised by the hot Jupiters, but the models that they have now appear to produce systems that have 5 to 10 planets as a normal thing, so that the number of the models that we have now seem to indicate our system is normal, but the models might be wrong. Right. So it's another good question, and the answer isn't known yet. Right. Some of these systems that we have found have three planets so far around one star. That's the record, I think, at this point, or 4. But don't know. Okay, question.
Can you give your definition of Earth-like? The term is bandied around in the reports so much that they have to have caveats.
Yes.
About saying, oh, but. So what's your range?
I was part of this science working group for the terrestrial planet finder, which was a space telescope array designed to actually get an image of and take a spectrum of an Earth-like planet. And so what we used for our definition was ultimately what we meant as a definition was not just Earth size and Earth temperature, but an atmosphere like the Earth's that's out of equilibrium, meaning there's a biosphere. Because if you looked at our atmosphere spectrum from outside and compared it to Mars or Venus, you could tell there was something wrong here. That there are processes that our oxygen, for instance, is not in equilibrium. It rusts the rocks and goes away. So the oxygen atmosphere shows there's a biosphere. So that was what we ultimately meant the terrestrial planet finder to be able to do, was not just Earth size, but an atmosphere that shows signs of the activity of life. That was the strong definition. Now, what people mean by Earth-like planets presently, they find one that's rocky probably and is sort of the Earth-sized and sort of Earth temperature. That's today's definition, because we don't have the technology to push it to really Earth-like.
Well, they're using it for the new discoveries that are still, 50 times?
Yeah, I think that the Earth-like is such an attention grabber that it's getting, I agree with you that it's getting used a little too casually, right? So the recent discovery 3 or 4 weeks ago of a planet that's Earth temperature and is only 5 times the mass of the Earth. So it's smaller than any of the Jovian planets, but somewhat, substantially bigger than the Earth. And it's it's definitely Earth temperature, meaning liquid water could exist on it. That's today's newest, closest approach to Earth-like, right?
You mentioned that SOFIA is not yet operational, and it sounded like it's going to be a while before it is. So what work remains? NASA Dryden's plan is to test it through more and more taxing maneuvers, because the airframe was weakened by taking a slice out of it and installing that telescope. So they've got the whole thing wired up with sensors for stress, and put it through more and more complicated maneuvers with the telescope door closed and the telescope locked. Then repeat with more and more complicated maneuvers with the telescope swinging. Then open the door, which the engineers are a little white knuckle about, right? Now, the wind tunnel tests say it should handle fine, but so there's gradually more and more challenging maneuvers, first with the door closed, then with the door open, before you finally let astronomers on board, anybody but test pilots on board, right? Because this is, cutting a hole in a 747, it's not something you do every day, right?
Do we know if there's a shepherding effect between Jupiter and the asteroid belt?
Yes, the fact that there is an asteroid belt at all is probably due to the fact that Jupiter got big and interrupted the growth of a planet there, stirred up the material so it couldn't combine and instead started shattering, right? So there are gaps in the asteroid belt that correspond to orbital periods that are integer fractions of Jupiter's period, and Jupiter clears them out by kicking them repeatedly. So Jupiter definitely sculpts the asteroid belt, and Jupiter maybe caused the asteroid belt. So I don't want to go out on a limb, but probably a big planet, the biggest planet in a system, might well have a asteroid belt just inboard of it, like Epsilon Eridani, right? There's reasons that would happen.
Yeah. Yes, sir.
What makes the inner planets tend to form rocky planets and the outer planets liquid or gaseous?
It's the temperature at which the material condensed. So the temperatures of the cloud from which the solids were condensing in the region where where Earth and so on are, that the temperature of the material there only allowed silicon and metal grains to become solid, basically, and then consolidate into a planet. Beyond what we call the ice line, which is just at the outer edge of the asteroid belt, beyond there, ice can be a solid in space. And so ice, which can include hydrogen, which is the most abundant element of the raw material, then you could make hydrogen-containing ice beyond the ice line, and so you could use like 90% of the raw material instead of a few percent of the raw material. So you get little bitty rocky metal planets where the temperature of the nebula was high, and you get big icy planets beyond the point where ice could condense as a solid.
Okay, and a second question, what puts all the planets and the other debris in a plane instead of being randomly distributed like the Oort cloud?
What you're seeing is as the original cloud collapsed under its own gravity and the spin increased, and the effect of that, and as the material would run into itself and average out its motions, you would get that the raw material that wasn't actually added to the sun would end up in a flat plane. And so all the raw material for the planets would have been in a plane to start with, even before the planets formed, by the expected physics of what happens if you take a slowly spinning big cloud and contract it down. You get a pancake. Okay. Is that the answer to your question?
Thank you.
Okay, yeah.
I had read recently that there's a proposal for a companion satellite when they get the Webb telescope operational that could be used as a coronagraph and possibly give TPF kind of functionality. You have any further data on where that stands? And
yeah, TPF no longer has a launch date. They used that money. NASA decided to not move forward with TPF. So a way to use Webb and make a coronagraph, because none of the instruments for Webb, as I understand it, are going to have a coronagraph, a little mask inside, is to have a little subsatellite parked out in front of Webb. And I don't know where the discussion is on that, but it would seem to be an inexpensive augmentation that could do some of the work that TPF isn't going to do now for 20, 25 years, maybe. Yeah.
Will they have a spectrograph where they could detect oxygen or something in atmosphere if they could image it?
If you put the coronagraph on, you can then look at the system with any of the instruments that are on Webb. It has an infrared spectrograph on it. Yes.
How soon do you think SOFIA would be operational? How soon would they open the door and fly it?
The expectation, right, the present schedule says the first open door tests are not until fall of '08, which strikes me as testing it a little too carefully, but then I don't, I'm not going to get on it until it's been, right? So that a year and a half until the first open door tests, and then it would be at least 6 months after that before somebody's trying to do a scientific measurement with it. Right. So into middle '09 before anybody's got a scientific instrument on board looking at the sky.
What will you be doing here in the meantime?
Trying to design the program for training the teachers to work with the astronomers. And I do the little bit of, writing press releases, making, literature, responses to queries from reporters, that kind of stuff right now.
Thank you.
Yeah. Let's see here.
How certain are we that Mercury itself is a planet and might not be something else? Because isn't its orbit a little bit off circular and a little bit scant?
Yeah, its orbit is tipped, second most tipped after Pluto's, but its material, its a composition that we can discern from its density is like an Earth with a big core and a small mantle, and so on. And so it doesn't have the it's almost the mass of Mars. So if you're going to start drawing the line, Pluto, an important point, Pluto is smaller than Earth's moon. And people perhaps don't realize that, how tiny Pluto is. And so Mercury, I think, is safe. I don't think there's any reason to plink that one out. Yes, sir.
I have a couple questions. One is, how expensive is this airplane telescope by comparison to other space-based telescopes? But you can hold that question if you like. The primary question I have, it seems like the Earth is very heavy because of the presence of iron. Now, is that something to do with the condensation area, the area, the temperature?
That's right. And yeah, go ahead, sorry.
And then how much of the presence of iron on our planet would be considered due to this so-called early impact of a secondary object? Is there any credence to that theory, that there was a secondary object about the time of the moon formation? Or?
You're referring to the hypothesis that was what formed the moon, was a very large impact early on, and most astronomers believe the evidence is strong that there was such a big impact, but you only needed an object 1/10 the mass of the Earth to do that.
But was there a theory also that it carried iron with it?
It would have been an object like the Earth, meaning an iron core and a silicate mantle.
Okay.
Yeah, so it wouldn't have added particularly, the Earth's iron core, the amount of iron in the Earth is just right for its position.
Oh, okay.
Yeah.
Well, that was the question I had.
Yeah. And Mercury has much more iron than the Earth, and that's consistent with its position. So at least for our, Mercury, Venus, Earth, Mars, the progression is just right in their compositions for the temperatures that we'd expect them to have condensed at.
And was there any argument about Pluto having a moon as to it might be considered a planet? That's my last question.
Alan Stern, who's an acquaintance of mine, is the principal investigator of the New Horizons craft that's on its way to Pluto, and he's very upset when you say that Pluto's not a planet. But one of the reasons he cites is, well, it has a moon, but asteroids have moons, and several of the Kuiper Belt objects have moons, so having a moon is not a special thing. But people bug Alan and say, hey, you're going to turn it around now that it's not a planet anymore? You can't. Okay.
I gathered that the stars that you discussed are single star systems, and I'm wondering what is the current thinking on what percentage of stars are part of multiple systems like Alpha Centauri, which is, if I understand, 3 stars. And I have a follow-up question related to that.
Well, your question, what's the majority of stars are in multiple systems. Debris disks have been found, and the earlier stage, the proplid, have been found in multiple star systems. But if the two stars are very close together, you'll find the disk around both of them as a unit. And if the stars are far apart, you find a disk around one star and maybe a disk or not around the second star. But if the stars are in some intermediate separation range, then you tend to not find disks. So there's apparently a danger zone, the wrong separation for a binary star system where you don't get a disk, but you can have stars real close together and a disk around both, or far apart and each one has its own disk.
And I'm sort of gathering that the reason that the ones you're looking at are single star systems is that it's thought the chance for a planet with a stable orbit like Earth would be much greater in that sort of a system, but it seems that still around multiple star systems you might get some very interesting and bizarre patterns or lack of pattern in orbits.
The calculation is that if a planet is either 10 times farther away from the two stars than their separation, or 1/10 of the two stars separation, then the orbit is stable. Right? So two stars 0.1 AU apart, then you could put the Earth around that and it would be fine. Or 2 stars farther than 10 AU apart and then put the Earth around one or the other, and that would be fine. It's the intermediate cases where you don't have a stable orbit for a planet.
Thank you.
You're welcome.
Let's thank Dr. Backman.
You're welcome.
That talk just ran rings around some of our other speakers. We appreciated that very much. Thank you all for coming. This is the last lecture of the year. We hope to see you back next school year for more of the Silicon Valley Astronomy Lectures. Good night.